Okay, Europa Clipper and beyond. And so we're going to try to cover ice-covered worlds all the way through to intelligence. Duncan is going to do the ice-covered worlds to intelligence part. I'm going to do Europa Clipper. Europa Clipper is a habit. Is there anything you need to know about us? I'm a polar geophysicist who 20 years ago got drafted into doing Europa because I understood radar over ice-covered worlds. And so I'm now planetary geophysicist, running the radar for Europa Clipper. Duncan was a planetary geophysicist working with Ken on radar over radar over Venus with Magellan, and then he's been drafted into polar geophysics. So he's a co-PI on the Science and Technology Center at NSF for looking for the oldest ice on planet Earth. He's also the technical director for the science data system for Europa Clipper, and we're half the data on the mission. So there's going to be a lot of data coming through University of Texas in a few years. We launched a year ago today, and they're laying off 11% of JPL today. So anyway, it's been a big, interesting year. Europa Clipper, let's just cover that. Europa Clipper is a habitability mission, so you're going to see a lot about exchange processes here. Europa's, got a global ocean, an ice shell, and a very intense radiation environment. Put all those things together, and you have interesting chemistry. So as a place for chemotrophic life to pop up, it's a good candidate. My advance. There we go. Good deal. Just to give you familiar, Europa surface is covered with stuff. Some of that stuff's endogenic, some of that stuff's exogenic. The surface is clearly created. There's all these linear features where stuff's coming from below, and it's destroyed. Stuff's going on, and the brittle crust on the outside is collapsing. There's plenty of modification too. There's exogenic modification from impacts, and then there's stuff going on below where it's clearly being modified subtly from inside. So we're looking for a home for life to begin. So we've got to look at the interior of Europa. Interior of Europa, like I said before, it's Earth. Okay, we have an iron core, rocky mantle, and ocean and ice shell. The ocean ice shell together is about 100 kilometers thick. That's, gravity tells us that from Galileo. I didn't go into all the things we knew about Europa from Galileo. Hopefully you've got that. But you think about that 100 kilometers, the gravity on Europa is 1/8 of Earth. And so everything scales. When we're doing the science validation for how to characterize habitability of Europa, it's mostly driven by pressure, temperature, and then the impurity content of the ocean and how that transfers into the ice. And so, so that 100 kilometers of ocean and ice shell is really only, it's really only a dozen kilometers. So the ice shell is 15 to 30 kilometers thick. The ocean's sort of 60 kilometers thick. But when you actually turn that to Earth's gravity, it's virtually the same as the ice-covered part of Earth. The thickest ice on Earth is 4 kilometers, and the thickest floating ice on Earth is a kilometer or 2. And so it's very similar. And what that means is that everything we've learned to do on Earth will apply at Europa, at least naively. Okay? Now, whether that rocky mantle has leached to give the same chemical distribution as our oceans have, the minimally astonishing thing is, so you're looking at chlorines to sulfate, maybe a little bit of ammonia in there. The other thing to know is that we have huge tides on Europa because of the resonant orbits of all of Jupiter's moons. The tides are 60 meters, so it's an incredible amount of energy going into the ice shell. We don't know if that energy is dissipated in the ice shell, in the circulation of the ocean, or in solid tides. You go solid tides, look at Io one step in, and Io is, ripping itself from the inside because of the tides. There's no ocean, there's no ice. Here, we don't exactly know what the distribution of energy is. So that's going to be something we really need to find out. Okay, characteristics. I just went all over all this stuff. We've got water, we've got the essential elements, chemical energy. What's important is the radiation environment is basically taking every neutral and turning it into an ion. We're right in the plasma sheet of Jupiter, and so we're you know, we have a linear accelerator pasting the surface of Europa with oxidants, and then if some of that tidal energy goes into the silicate mantle, you know, and then it means that we're going to get a load of reductants, not unlike Earth. You know, the metals will be coming up. So we have a farm for chemotrophs, and it's been sitting there for 4 billion years. Okay, if there's life in the solar system and this hasn't actually hatched it, you know, that's why I'm there. I'm an Earth guy, but Europa is the only place I would spend my life, which I have, actually, it turns out, getting to. Okay, now we're down to mission science. You're going to hear a lot, you know, in the press you'll hear a lot about the composition, the geology, the activity. We do have, that's kind of worth pointing out. No, I did it wrong. I always do it wrong. Yeah, the activity, remember, Hubble has seen, the UV frequencies of Hubble have seen nice oxygen-hydrogen spikes for Europa. So there's a good chance stuff's leaking out somewhere. We think it's ephemeral. The chances of us intersecting one are probably not really very high. But it will contribute to the atmosphere. So we really do need to understand the composition of the atmosphere. And then ultimately, we're going to land. And so our instrument, we'll get there in just a second. Our instrument will be very important for all of these things. But in the end, I'm personally responsible for the ice shell. And so that's me, you know, which is kind of a great thing, if you can imagine. Here are the investigations. The remote sensing investigations in frequency order. So we have the ultraviolet telescope, which is the plume thing for oxygen, hydrogen. The cameras, we have lots of cameras, and infrared spectrometer and a thermal imager, so a long wavelength. And then here, you'll notice we have the whole subsurface, and which is really lovely. So it's the ice penetrating range. It's all done out of UTIG. We have about 10 institutions who are attached to us, and then we're using both JPL and APL. JPL built the instrument, APL will be doing the experiment planning. So that's kind of where we are. The rest of the mission, these are composition guys, the mass spectrometer, and we have a dust analyzer on it as well. And then of course, without the, this is a magnetometer, and then you've got to have a particle and plasma instrument to basically make corrections to the magnetometer so you can use the gravity to invert for the structure and the conductivity of the ocean, all that kind of stuff. That's planetary geophysics, but sort of in the one-dimensional mode. And then we're bringing radar to it. And I'll show some pictures here to complement this stuff to let you know that we're bringing the third dimension to planetary. So ice-covered ocean worlds we can look into. Ice is transparent to VHF. And so we're flying VHF radars, and we can see through kilometers and kilometers of the stuff on Earth, and we can probably see through tens of kilometers of the stuff on Europa. Okay, this is just, we knew there were going to be lots of engineers in the audience, so we threw this one in. Solar panels, there are 10 of them. It's about the size of a basketball court. If you remember Galileo, the instruments pointed every which way, and so there was lots and lots of negotiation about what to point to. We have a nadir pointing deck with all the instruments looking down, except for the RAM instruments, the compositional instruments need to look forward. So that's all been done, the design. We did not make Galileo's mistakes, thank goodness. And then the radar antennas, we have a pair, one on each panel, solar array. They're 16 meters, and then we have an interferometric array of shorter wavelength. So we have an HF hanging out at the end and an array of VHFs in the middle. So we're a SAR. We can look left and right. It's very, very important when the surface is rough. Oh, and then magnetometer. And it was supposed to be a nice, tricky magnetometer, but a scalar. But in the end, it's a pretty boring. It's a pretty boring flux gate. But it's got 3 components. It's moderately nice. It's a nightmare to calibrate. Okay, the way we did Europa, when Europa was originally proposed, we were going to go into orbit. The Europa Orbiter mission back in the late 90s, I was PI for one of those instruments, and it cost billions because every chip had to run in the middle of a nuclear reactor. However, we came up here at UT, we came up with the idea of basically orbiting Jupiter and then diving in. And so instead of spending months and months in orbit around Europa, we spend minutes and minutes diving through the plasma sheet. And so what that does is that gives us, we come by every 3 weeks and for 3 years, okay? And so, so we collect radiation very slowly. And this is, you can tell in this diagram, this is the anti-Jovian campaign, and this is the color code is collecting radiation. So blue to orange, orange is 1 megarad. And so this is anti-Jovian Europa, then you crank over the top of Jupiter, you do it all again, sub-Jovian Europa, and then you're murdering yourself on the way out. We're all turning red. And so that's 50 flybys. And then when you put it all together, those 50 flybys give us a grid. And that grid is essentially what we would have gotten with an orbiter in 60 days, except it costs half the amount of money. We got down to $2.5 billion. And then the interesting thing about this is the data volume I mentioned before, that each one of these flybys is a New Horizons mission. Okay, everybody remembers New Horizons flying by Pluto? We're going to be flying a New Horizons mission every 3 weeks for 3 years. So the intensity of that is almost unimaginable. So that's why Duncan gets, you know, he's responsible for keeping the trains running on time. Okay, let's move on to the radar. And I'll try to show you a few examples of the radar. And I'm doing pretty well. So this is the, again, we're a habitability mission, and we have this really complicated stack of tectonic facies on Europa, you know, and our whole goal is to understand the exchange. In other words, how the ocean talks to the ice, and how the atmosphere talks to the ice, and how they talk to each other, and where do they get together, you know. There's a lot of oxidants on top, a lot of reductants in the bottom, and where they get together, you've got the energy for chemotrophs. So the formal investigations, what we're going in to measure with, 2 frequencies, 9 megahertz, 60 megahertz, shallow subsurface water structure, ice-ocean interface, the subsurface thermophysical properties, material exchange is everything for habitability. We're also the altimeter. We threw the altimeter off. That was $100 million. And so the radar is the altimeter. With 60-meter tides, it should work out just fine. And then in the end, we're also responsible for picking landing sites. So we have a whole scheme for how to do the near surface characterization of the porous ice regolith. Nobody's ever done that before. The first question you ask about Europa, well, how porous is it, how deep? And these radars, we do this on Earth all the time. We can figure out what the porosity versus depth is down to several hundred meters. And so we will have better knowledge of landing sites than any other mission that's flown. Okay, this is how we talk about it. Now I'm only going to cover, we're tight on time, so I'm covering the bottom 3. Again, this is what you just saw. The interesting thing about it is that the thing important to remember about the ice-ocean interface on Europa, it snows up. It snows up. On Earth, on Mars, it snows down. On Europa, it snows up. In other words, that ocean supercools, and whenever it supercools, you get ice crystals. Those ice crystals reject the impurities. They're always buoyant, and they float up. And then they accumulate at the bottom. So there's accreted ice at the bottom. Okay, so that is how you add mass to the Europa shell. And the nice thing about that is that's bringing the impurities in the ocean up into the ice shell. Okay, now how does it go down again? I'll show a couple of pictures. We think we know how. And so as it goes up, the interesting thing about it is it brings the heat of the ocean up into the ice shell. So you're having a thermodynamic instability coming up into the ice shell. And that ice shell is saltier than this fresh accreted ice you have, which means that you hit the eutectic and then brine pockets form. So the near surface of Europa should be coated with brine pockets in the shallow subsurface. Now we hypothesized that about 10 years ago, and then we went out and looked for it and we found it. I'll show you a picture. So there you go. So we're going to talk about these 3 radar domains. Now, the science team has never, ever had access to the third dimension. And so we have to have this nomenclature to teach planetary scientists who work on the top 3 microns how to work on the top 3. How do you test hypotheses in the top 30 kilometers? And so that's our particular challenge. We do it on Earth. Duncan will talk a lot about that. Okay, and this is what it looks like. This is a more complicated version of everything I've been talking about. Here are the plumes coming up, and here's that eutectic where brine starts to form. Here's a deep one, here's a shallow one, and here's the thermal profile. The shallow one is thermally conductive, cold on top, warm on the bottom, not much going on, nice temperature function. However, when these plumes come up, then you're dominated with ductile behavior. So we've got to understand this ductile behavior. These things are ephemeral. They come up, bring the heat up, then they cool down, okay? Which means that for 4 billion, no, it's not 4 billion years, the surface is only 60 million years old as far as we can tell. So for 60 million years, these things have been coming up, freezing, and staying in place. When it's cold, we can see through anything. When there's brine, we can't. And so our whole program is looking for fossil plumes that have frozen out. And so that's what this instrument was designed to do. So how do we test whether those hypotheses are valid? We go to Antarctica, okay? And this is a thin, brittle shell in Antarctica. You can see where it's been snowing from the bottom. This is the accreted ice under one of the ice shelves in Antarctica. It's only a few hundred meters thick, so it's equivalent to a few kilometers on Europa. And so this is the thin, brittle shell analog. And if anybody's heard about Lake Vostok, it's the biggest subglacial lake in the world. And I've always said it's not a very good Europa analog. Boy, was I wrong. We get the same kind of accretion. We flew Lake Vostok 20 years ago. And we get the same kind of accretion. You can see it. And let's go back here. Yeah, and the interesting last point to make here before I go to show the pictures of Lake Vostok is this is the salinity. When basically as the ocean gets saltier, you can't read it, but the ocean's getting saltier, and as you go down, the blue is the frequency of brine pockets. And we wrote a whole article on the best signature of habitability for ice-covered worlds is the concentration of brine pockets. Okay, and so if we can figure out the concentration of brine pockets, we have an indicator of astrobiological potential, okay, for a chemotrophic system. And we can do that remotely by flying by. Okay, next. And this is Vostok again. When we make a map of that accreted ice, it's a few hundred kilometers, about the size of Lake Ontario. And this is the accreted ice. You can see it. Isn't that cool? We can see accreted ice. We'll be able to see it on Europa. It's the same frequencies. This is 60 megahertz. And then here's a cross section. It's about 4,000 meters thick. It's about 100 kilometers across here. And you can see the accreted ice forming. But the interesting thing is, in Antarctica, the ice is flowing from uphill on the left to downhill on the right. And you can actually see that the gravity is pulling that ice up over the mountains, and all of that accreted ice is being excavated up over the mountains. Okay, if you turn that on its side, that's essentially the same as the accreted ice coming up one of those plumes of Europa. So the stress and strain in this ice should leave a signature in the fabric. It's a monomineralic substance. How do you find fossil tectonic activity? The crystals reorient whenever it's strained, and whenever the crystals reorient, it's birefringent. The dielectric properties change, okay? And that's what this is. Here are birefringent bands over Lake Vostok showing us that the crystal structure in that monomineralic material are changing in response to the stress. Flip Lake Vostok up on its side, and it's a diapir on Europa. You use the birefringent bands to evaluate what the strain history is for that, and you can test hypotheses for exchange with ductile motion on Europa. That's where we are. It's working. Okay, we hadn't even seen these bands, you know, when we wrote the Europa proposal. And I'm just about there. Last analog's brittle shell. This is where one of those plumes is coming up, and we predicted that wherever there's a water body under here, the matrix, They come up, they thin the lid collapses, and then, the lid collapses, and then you basically are exposing all of the oxidants in the near surface with whatever came up in that plume, in the reductants. And so this is essentially a Cuisinart for chemotrophic, for fluids that can host chemotrophic life. We don't think they're hosting them in the surface, but these fluids probably go down. And then who knows where the best is. So we won't go into the details, but on Earth, we see collapsing ice shelves like this all over, and then we see refreezing of those collapsing ice shelves, just like we see on Europa. So everything we see with the destruction of the brittle shallow subsurface on Europa is represented on Earth, and we basically had, we've collected data over 20 years over Antarctica, so these are all of the places we have to go look. We have 5 years before Jupiter orbit insertion, and so we're going back to these data volumes, and we have marshaled the freaking world to fly our radar over Antarctica for the next 5 years. We have 3 DC-3s and a helicopter sitting on the back of a Korean icebreaker. And we use these things for the standard climate change studies for Antarctica, but virtually all of those studies intersect what we need to do science validation for the Europa radar, using those radar domains I talked about before. And Duncan, hopefully I didn't go too far over. We're back to Earth.
So, yeah, taking a little bit of a diversion, and I'll go over this quickly, but yes, this is Earth, and then down the bottom there is Antarctica that we're just talking about. Earth is also an ice covered planet, so it's going to take a quick diversion and just looking at this from the point of view of the topics that I think of this conference. So lots of ice there, and we live in an interesting point in Earth history and with relationship to intelligence on Earth, this tiny little fraction at the end of this long history of lots of pretty boring stuff going on. But if we zoom in on that last little bit, when we actually have complex life, you notice that right at the end in the temperature records, it starts to get cold right in there. And then moving on, this is a climate history of the last 5 million years when humans are arising, and you'll notice that the frequency of what's going on here rapidly changes over time, and the amplitude of what's going on. This is a mix of the signal of temperature and ice volume on Earth from ocean records. And at this point here, we nearly went away due to these extreme variations in climate that have been happening pretty much in the last million years. Now, what's been driving this? It's ice. We have records from the ice cores. We're starting to go back to on the order of 1 million years. I'm part of this NSF Science and Technology Center that's been looking for that on behalf of the US program. A decade ago, we went to a place called Dome C, searching, using the radar on this 1945 DC-3, which is the prototype for the one Don was talking about that's on Europa Clipper. We used that to look for an ice core. That ice core popped out in January, which will hopefully have a climate record of this critical time in human evolution and, you know, the evolution of intelligence on Earth, which is currently, they just melted the last ice in the labs in Europe. So hopefully the next year we'll be finding out more on that period of time. But ice is a remarkable thing, made of the most common elements in the universe. It's polar, so it makes it sticky, and liquid at temperatures that life likes to be at. So that's great, but when we turn it into a crystalline form, solid form, it turns inside out. It's actually less dense than the liquid form, which is kind of weird if you think about it, but it means a lot of feedbacks are possible that really are important for both Earth and for the icy moons. And also comes out in this hexagonal structure, which snowflakes, a lot of edges, makes snow and ice very, very bright. So potential for a lot of feedbacks. And we see this in the climate record of the Earth's history. I mean, this moment in time when we don't have giant ice sheets in North America is an anomaly. Over the last 1 million years, we've had these ice sheets going back and forth, growing, and then abruptly collapsing. And this is because of these feedbacks, ice acting as basically a transistor for the climate record. Ice darkens as it melts. These edges start going away, and so it becomes hotter. ice melts under pressure at the bottom because the more denser form wants to get into the more denser form. And that causes erosion at the bottom, which digs a big hole, and then ice wants to float because it's less dense. So the ocean wants to get into the hole under the ice sheet and collapse them. So we have these strong positive feedbacks which are driving that strong oscillation in the climate record in the last million years. And this has produced interesting results. If we look into the paleo records for what's going on with sea level in the past, as we came out of the last ice age 20,000 years ago, we've had up to 20 meters of sea level rise over the period of 500 years. So that happened 8 times over the last million years that our ancestors had to respond to these huge changes in what happened at the coastlines of the Earth. And may have been something that was a driver on intelligence or that happening. So moving on, just thinking about where this is in the broader context, going back, this is really kind of the first moment in time, this last million years, where we've both had continents which were arranged with large amounts of coastline, everything was fragmented, and big ice sheets moving around. So, well, no, we have a discussion on the Fermi paradox later on this afternoon. I mean, that may play a role, this moment in time, why over the past 300 million years we've only had intelligence pop up once, although there might be some commentary on that in the panel. And then moving on, back to the icy moons of Jupiter. How does these feedbacks for ice behave there? So we have Io, Jupiter's closest to Io. It's pumped up, it's dry, it's magmatic. You got Europa with kind of 100 kilometers of water, as Don was saying, on top, and Ganymede. And so they're all conjoined. What happens in one propagates through these orbital resonance to another, and then Callisto's off being weird by itself out on the edge. And it's pretty much undifferentiated, unmelted by these processes. If we look inside, it turns out that Ganymede's large enough that the pressures drive the ice into new forms, not the hexagonal form we were discussing before, but a denser form which actually sinks to the bottom. So that can choke off the interactions with the rock which are needed to fuel chemistry for life. And so that's an active field of research. There's actually going to be a European mission that's going to specifically study Ganymede, and Don's involved in the radar for that mission as well. Europa, we're kind of in the sweet spot where we're still in the space where we've got the ice that's floating on top, and we have these potential for direct ice-rock interactions. And then there's also feedbacks that might stabilize the existence of the oceans in the world, like Europa, where we've got ice, and if we melt it, we change the dynamics of the system and get more melting, we thin it. That means we have less pressure on the ice at the bottom, and we get freezing and accretion on the bottom, and thus we get back to the stable path. If we thicken the ice sheet, we cool things down, the ice is going to get thicker, higher pressures, and that will cause melting at the bottom and injection, and again, an ice shell, but maybe with some more interesting chemistry in it. So the takeaways up there, I think we're at 0 time, but we're exploring the habitability and potential rise of intelligence with things going on right now with Europa in a few years' time, and then on Earth with these ice coring efforts. We've got these critical feedbacks of water ice. Water is fantastic from that point of view for evolution and habitability. And then we've got lots of lessons that we can learn from the ice sheets that can go for the icy worlds, but also vice versa. So thank you.